Yeah, I would like to tell you about our experience at Sanas with using Dagster and various Dagster's abstractions for various tasks. So one of them is offline batch inference. Um, so we at Sanas are doing a real-time voice accent translation, for example, from Indian accent to British accent. And in order to do this, we are training like a few neural networks, which usually they usually consume some other neural networks outputs, features, or like embeddings, right? So we have a need to for the training process, we have a need to calculate these embeddings or features, or this might be just some normal statistics regularly as part of our like weekly ETL or maybe daily ETL or something like this. So we're using Dagster to orchestrate our ETL and the trainings too. But basically, this talk would be a collection of experiences or maybe advice that I can give on this topic, batch inference with Dagster. Yeah, so let's go to the next slide. So just to make it clear what we're dealing with here. First, we are using AWS Kubernetes on AWS. Our data is located in two locations. It's S3. This is usually for backup and also internal processing in the ETL. But we also have another location called EFS, which is basically like a scalable file system provided by AWS, which we use for trainings because it's way more performant than S3. So we need to keep like two copies of our data, of most of the data that we use for trainings at both S3 and EFS. This is a major thing, and it may like become really hard to copy and sync, files from one location to another location. So this is important because we'll be dealing with this later. Then we may receive like arbitrary amounts of data at arbitrary time, maybe once per week, but we want to switch to once per day. And we may be receiving either new deliveries of new data which we haven't processed before, or maybe we would have to like rerun processing on all the data that we already have in case we want to change something in the how are the embeddings calculated or something else. So we may be working with either, I don't know, thousands, tens of thousands, or millions. Like right now we have 10 millions in total of audio files. I mean, they are quite short, usually like from 5 to 20 seconds, but it's still a lot of data. And because of this, because of the varying data size we need to process, and because of the overall scale, it's clear that we need some sort of horizontal scaling here, right? We cannot be processing this like on just one instance or something like this. So we need to solve a few problems. First, we need to keep track of the process files because we didn't want to be processing the same file twice. It would be really bad, especially if this happens like on a scale of, I don't know, a million files, right? So we need to keep track of the process files somewhere. We cannot just have them sitting on S3 or on EFS because listing this is like, it's impossible. It will take like a few hours just to list the files. So we need like a database or something else where we store the metadata about the process files. Then it becomes hard to use an IAM manager for something like this for a few reasons. First, we cannot return the actual files by the IAM manager because it's too many of them. So we want to return like metadata records about the files, something like this. However, the IAM manager only works when the step has finished. And if we have one failure in the step, nothing will be written, right? There are some problems with idempotency also when writing results like this with an IAM manager, because basically if we run the job, we don't want anything to change in the external storage. However, if we do some appends to some external database or something like this, we need to make sure we do not like append the same information twice and stuff like that. Another problem is a circle dependency on the same asset. If we want to rerun the job, we first want to check which files did we already compute, filter them out, and compute the rest. But it becomes a little bit hard with an iManager, and Pyrite was so strict about accessing the same, for example, accessing the definitions object inside the asset, because Duckster doesn't directly allow circular dependencies. So we had to do it with definitions.load asset value. But Pyrite was so strict about this import that we had to hide it behind an import lib call. Anyway, so basically what I'm saying, there are a few problems with using the iManager for that. Not everything has to be an iManager. So this was the first lesson I learned during implementing this. Actually, what we need here is a resource, not an iManager. So let's say we have a resource which can do two things. First, it can save a file or a feature or whatever in multiple locations at the same time. In our case, it would be S3 and EFS. And then after that, it would append a record to a database about this file being successfully processed. So this, I would call it a feature store. It is like very similar to a feature store. This feature store can be exposed as a Duckster resource. It makes it very clear where does the data stay for every asset, because we can see it in the configuration of this resource. And it can be used easily from the code, like in this example in the screenshot. Next slide. So, for example, this is the example of this configured resource. You can see it has like two data locations, S3 and EFS. It has the feature name, and it's like very easy to understand where is this, in which assets is this used, like on the right side. So this abstraction makes a lot of sense, and it was like way easier using it than an iManager in my first implementation. Okay, next slide. So yeah, basically what we do is we iterate over like a batch of files. We will talk about how do we do the batching later, and we just call the feature store that like write something, write in the array, write tensor on like in a for loop. And then the asset does not return like it may not return anything. That's totally fine. We're not using a manager here. Okay, next slide. And so regarding to tracking files and filtering files that haven't been computed yet, we went with the basically Duckster's approach for data versions. I liked it a lot. So basically every feature has a set of upstream features it's computed from, and each of them has its own data version. So what we do is we like stick them together, hash them, and then also add the code version, hash it too, in case it changes. So what we achieve by this is before running a processing, we already know the data version for every file, and we may filter out the files which already have been processed previously if the data version did not change. Yeah, and that's a really useful thing to have. And then the feature store just has a general method which can take a data frame of files to process and a set of upstream feature stores, and it will automatically compute these data versions for every file and filter out the files that don't need to be updated. So the first part was how do we store all of this in a convenient way? And the answer was a feature store and the custom Duckster resource. The second part is how do we scale our batch processing? So the first attempt was to use Duckster's dynamic ops. It's easy to implement because you don't need any additional infrastructure. Duckster can do it out of the box. You can like easily spawn 100 or 1,000 dynamic ops, and each will run in a separate Kubernetes container pod. Yeah, they will run in parallel. There is a good thing about it. Like you can see the progress pretty clear from Duckster's UI, and you can even restart failed steps if you need to. But however, there are also a few cons. For example, this approach only allows very simple parallelization patterns like fan out or fan in or something like this. Like if you need to, it's easy to use if you need to just do like batch processing. But if you, for example, need to do a group by, suddenly you need a Spark cluster or something like this to do it because, well, that's only so much like Duckster can do about it. So our first attempt was doing this, and it worked okay. There were some problems with scaling this to, I don't know, more than 3,000 steps at the same time. This is where Duckster's orchestration overhead becomes noticeable. It may take around like from 30 minutes to 1 hour just to start all of the steps, like create all the pods, and a lot of overhead is happening. The second approach we came to was using Ray for scaling. So what is Ray? Ray is a general purpose like distributed engine for Python. Basically, it's similar to Spark, but you can run arbitrary Python code and parallelize it across a cluster. Uh, and Basically, it's an ideal fit for our needs. Uh, the another advantage is you don't need to do dynamic ops anymore because they do complicate the code. They introduce these graphs that you need to manage. But now instead with Ray, we have just a single op. It's a single step. The code is very simple Python code. It's basically just a few additional decorators on top of some functions, and they just get executed remotely. There is little to like zero orchestration overhead, uh, because now instead of doing the parallelization on the on the step level, we're doing it instead on the like data level, or you can call it maybe process level. Because what Ray does is basically you have a data frame and then it splits it to parts and then sends to different remote workers, and then they execute their part and send back the results. And all the scaling happens behind the scenes. Uh, Another advantage is having resource-based scaling. So if you're doing the dynamic ops approach, you need to specify the steps need to be specified in advance, like how many of this dynamic ops do you want to run, for example. Uh, with Ray, instead, you can specify the resources which a step needs, and Ray will figure out how many pods does it need to start for you to scale your workload, like to gather enough resources. Is it GPUs or CPUs or memory? Um, there are some cons like, yes, you need to get used to Ray, need to read some docs and dive deep to Ray, and you need to set up some infra. What we did is next slide. Is a custom Ray cluster resource. So another example of using resources in Duckster, which basically does all the heavy lifting for us. So the idea is this resource takes some information from Duckster. For example, what image are we running on? What are some Kubernetes abstractions like that we need? For example, do we need to mount any volumes or something like this? So it takes all of this from Duckster Kubernetes config, and it translates it to Ray. And then all you need to do in your asset is just to add this, like in this example, add the Ray cluster argument, and Duckster will automatically start a Ray cluster for you. In the code, you can start like just calling Ray functions, and you can connect this cluster. You can view look at what's going on there. Basically, the usage is super simple. But setting up this resource was quite complicated, and this is the infrastructural overhead which I was talking about. We probably have plans for open sourcing the Duckster Ray integration. It's not ready yet because there's a lot of like some specific stuff inside. But potentially, what you could do is like plug in this argument with the resource, and then it will take all the information about like internal Kubernetes stuff from Duckster and create a Ray cluster for you automatically with like the same configuration as your Duckster pods would have. Okay, next slide. And then using Ray for scaling is really easy. For example, this is how you do batch processing. Like this is basically all you need. There is no like any complex code here. It's like 10 lines of code, right? So instead of writing Duckster graphs, you can just do this. Okay, next slide. And then another good pattern we found was building an asset factory for all of this stuff. So in this image, you can see group of assets. They all belong to the same feature processing. Like the first asset is the actual feature processing, and the rest are like other information. For example, information about which files have failed the processing, and which files have passed the processing and then there's also array timeline exported, which it's the image you can see below. It's basically granular information about how long does which step in your code take to run, which is really convenient to see it after every like processing run in Duckster. And what we did is we built an asset factory for all of this, because we have many features we need to calculate. And basically, the only thing that is different is the processing step, like the actual step that gets mapped to a batch. So you can just use this asset factory and like spawn a bunch of different features. And the only thing that would be different is the processing function. And it's written in a way that you don't even need to know it's using Ray to scale it. Like you just write a Python function or a Python class in case you need like a stateful array actor. And then it will do everything behind the scenes. It will create this Duckster assets. It will use Ray to parallelize the stuff. So pretty powerful pattern. Yeah, next slide. So basically, that's it. Like I said, just a collection of insights we had. The first thing I learned is the AI managers are not always necessary. I spent a bunch of time trying to do this through AI managers, and it just using the resource is so much easier in this case. Then Ray is pretty good. We had some problems with it. There were some bugs, and it's a little bit early, but overall we managed to figure it out, and it's now like it's being able to scale our workloads and launch like hundreds and thousands of pods. And what else? Asset factories are pretty cool. Use them if you have lots of similar assets. And another thing which I did not talk about, because I understand that's like already a lot of information, is the branching AI manager. Just take a look at it. It's hidden somewhere in Duckster's code, but take a look at it. It will allow you to do testing in your branch deployments by automatically loading production assets if they're not materialized in the branch. I didn't have time to talk about this, maybe next time, but just highlighting this name to your branching AI manager.
Cool. I have a question. So if like one of the files in Ray fail, does Ray provide that information of like the specific, task or something that failed?
Mm-hmm. So what I do is, if you go back a few slides back, yeah, this one. So what I do here is no, Ray. So I mean, yes and no. Ray will show you logs, but by default, the processing and you can do stuff like add retries to tasks and things like that. But because we are usually handling a batch of files inside a single Ray worker, we have to do this ourselves. So we basically have a try except statement here, and we loop through the batch that the array worker gets, and then we do try except, and then if everything is okay, then we don't need to do anything. And then if there was an error, then we log it and we append the bad file name to the list, which in the end gets outputted from the Ray code. And this is like a valuable piece of information. So we store it in a separate asset, which is called failed files.
Okay.
And then in the result, for every file which failed, we have it in the data frame. We have the failure reason. Because there may be a few, maybe like the most common are read failed, write failed, like compute failed, and then there are a few more. You can like add specific failure reasons for specific features. And then also we have a trace in the logs for this file name. So we can go back to Duckster. Ray logs get written to Duckster standard error, which Duckster captures. So we can go back and look for this file name in the logs and see the exact error which happened. So this is what we do.
Cool. Thank you. We also got a couple questions in the chat. Um, so question about fanning in and fanning out, as well as do you have a side-by-side comparison of Ray versus Spark in terms of performance? And then a couple other ones.
Hmm. Yeah. So, what is fan in, fan out? Well, it is when you have one task which produces like n other tasks, or the other way. Uh, it's
Yep.
mostly our pattern that we have, but like once we also had to do a group by, and we were lucky to switch to Ray for parallelization at this point, because uh, like we couldn't do the group by, but using Duxer for parallelization, right? You would need to use a proper uh, like data frame processing engine like Spark or Ray, because Ray also has Ray data sets which are very similar to Spark. Uh, in terms of performance, I'm not sure. I don't think they are like they don't do the same. Like Ray is way more flexible. You can run like arbitrary Python code there. So there is no. I don't think there is a need to do such performance. If you just need to manipulate data frames, then like Spark should be enough for you. Ray is like more flexible. It does more things. So it's totally possible that it's slower. But actually, in the latest Ray version, I saw they now allow to use polars for the internal processing which is happening inside, which may speed things up. But also Ray is written in C++, like all the internal management that's going on there. So it should be pretty okay with performance. Um, what are the other questions? Um, yeah, how to write to if okay, I forgot this thing. So what our feature store does is when you write a feature with it, at first, like it can write it on an arbitrary list of locations. Like right now, we only have two, but potentially in the future we may have more. Right, it will just iterate over the directories where it needs to save it. We use universal path flip, so it abstracts the actual file system. We don't care. We just have a list of universal path flip paths, and we write the file or a numpy array or tensor or whatever in all the locations, and only after that we append the record to the database. Uh, so if a record is inside our database, it means the file has been successfully written to all locations. What database? We're just using Postgres. It's enough right now. We don't have any issues with that. Uh, we also use a RDS proxy for the Postgres database, so which like increases the amount of connections we can maintain in parallel. Uh, like running maybe dozens of thousands of pods at the same time is all right.